what we discussed last time. We were doing this. What did we first talk about? Sorry. So we know if you have a matrix A that's square and diagonalizable, then we can write it like this. We can diagonalize it like this. But what if it's if this is n cross n? What if A is m cross n? Or put it another way, so this is similarity transformation. This is for square matrices only. What if you have rectangular matrices? Do you have a, something an operation like this? Right. We do have the EQ variant. I think it's called equivalent transformation. I might be wrong. So we can relate A and another matrix AW, where we are working with two different bases for the input space and the output space. And how are they related? W here is it? Okay. And these two are called equivalent matrices. And I think this is correct. Yeah. Okay. Okay. And the reason we started talking about is when we have square diagonalizable matrices and you do similarity transformation, you can make the matrix A look as simple as possible, right? So we were asking, can we do something similar for rectangular matrices? And that led us to SVD. And if you have a matrix A, just for now let's say P cross Q. What is, okay, and what are the different terms? What is the size of this? Yeah, but what is the size? Okay. Right. Okay. And what are other additional properties of these two? What is the columns of U form an orthonormal basis for what? RP. Okay. Orthonormal basis for P. Right. Columns. For Q. And this one. What form does it take? Well, it cannot be diagonal because it's at least this form. This is diagonal, and everything else is 0. Okay, and sorry, D is diagonal. Yes, this is diagonal. Okay. Now, if the rank of A is R, then what else? What can we say about sigma? So this will be 0, 0, 0, 0. What is B? Will be R cross R, and you will have, this is diagonal, 0, and the convention is we always, well, yeah, sigma 1, sigma R, and this is greater than or equal 0. Okay. I think this is where we start, and what is how do we obtain U? What is eigenvectors of what? Yeah. Suppose and V. And what about sigma 1, sigma R? Well, of what? A transpose or A transpose A? Same, doesn't matter. A transpose A or A transpose, because eigenvalues of A and A transpose are the same. There's just one, well, we'll see. Well, one question, if A is rectangular, what is the size of A transpose A? What is the size of A transpose? Yeah. Sorry. How can we say that the eigenvalues of both of these are the same? But how many eigenvalues does this have? This one? P and Q are not the same. But I just said, well, the eigenvalues of both of these will be the same. Yes, they are symmetric. Sorry? Thank you, sir. So yeah, you're right. What will happen? What do you think will happen? So that means there will only be. Sorry? Right. R is less than P and Q. Right? The rank is R. That means you will have R non-zero eigenvalues here, and you will have R non-zero eigenvalues here. Everything else will be zero. The non-zero eigenvalues will be the same. Okay. I think this is where we stopped last time, right? Okay. We'll try and understand this a little bit more. The rank is R. P cross Q. Now let's divide U and V like this. Into two matrices U1 and U2. Yeah, V1 transpose and V2 transpose. And the division is such. See, this is of size R, right? This is of size R. What is this size here? How many columns do we have here and how many rows do we have here? No, here. You're right, Q. This will mean Q minus R here. Let's see, we divide this so that there are R columns first, and then Q minus R here, then R rows here. Now let's say we have Y equals A times X belongs to R Q. This is equivalent to saying you're doing U sigma V transpose X. If you expand this out in terms of U1, U2, D, V1, V2, well, this is a side note for now. If you multiply these out, what do you get? Let's keep the first, this one, same, U1. Okay. Let's keep the 0 as well. Okay. What about the bottom? That's it, or will you have another one here? Okay. And if you multiply this out, so you'll get U1 D U1 0 U1 transpose, and then you'll get, I'll write it here, U1 0 U1 transpose U2 0 . Oh, sorry, yes. Okay. This is okay now. This one's V2, yes. Okay. See, now let's try and understand what's happening here, right? If you multiply here by x, right, then the x would appear here in each of these terms, And what you're doing here, this is V transpose of a orthogonal matrix. That means it's V inverse, right? And V1 transpose X simply gives you the components of X in the R-dimensional subspace spanned by the first R rows, and then V2 transpose X gives you the components of X in the Q minus R dimensional subspace spanned by these rows. Okay. So now if you look at what happens to this V2 component right here, right? Anything that involves the V2 component gets multiplied by a 0. Okay. So whatever component of X is present in the subspace spanned by V2 gets zeroed out. It gets removed. Okay. That's with this. Now if you look at this, right? Yeah. Anything that involves U2. So U1, now whatever component is in V1 gets multiplied by U1 and U2. Okay. That's what you see. dV1, let's know that any component in V1, right, gets multiplied by U1 or U1. Now, any component here, any term that involves U2, the columns of U, gets a 0. Okay, so this means, and what comes out here, if you multiply X here, has to be in the column space spanned by this, right? And the subspace spanned by the columns of U2 gets zeroed out. That means you cannot get anything that is spanned by this P minus R columns of U. Whatever you will get out here has to be in this subspace, this R dimensional subspace. So that means one way to interpret what you see, these R columns here and these R rows here, these P minus R columns and these Q minus R rows, is that this and this together are what give you the non-zero values of whatever you get when you do AX. That's this term. Okay. Whatever is in this part of your input space gets zeroed out, and you can never get anything involving this subspace with the component in this subspace. Means this is simply this is an orthonormal basis for, or these Q minus R rows form an orthonormal basis for the null space of A. These form an orthonormal basis for what? The row space of A. U1 forms an orthonormal basis for the column space of A, and then this is that's the interpretation of these the columns of U and rows of V transpose, or columns of V. Okay. So effectively, even though we've written it like this, your U sigma V transpose is simply U1 d V1 transpose, and that's this is called the reduced SVD. Okay. And if that is the reduced SVD, A, you have U1, not sigma, D V1 transpose. What is the size of this? This is R cross R now. This is P cross Q. This is P cross R. This is R cross Q. Okay. That means if you take A and if you represent the input components in terms of the orthonormal basis for the row space V1, and you represent the whatever comes out in the orthonormal basis formed by U1, A and B are equivalent matrices. Okay, so if you choose to work with the V1 basis in the input space, at least for the row space, and U1 basis for the column space, then D is simply the operation that is happening. And since D is diagonal, okay, this is a way of diagonalizing our an arbitrary rectangular matrix but in fact, because it's rectangular, you have to work with two different bases. Okay. Right. We'll do a couple of examples and then we'll quickly move on. Let's say A is 1, 1. What is the SVD of this? Well, we want to find and we know how to find U, V and sigma. To find U, we need to find the eigenvalues and eigenvectors of this, and to find V, can you tell me what are the eigenvalues and eigenvectors of this? What will this be? This is easy, no? What is the eigenvalue? It's 2, eigenvector. It's simply 1. What about here? What are the eigenvalues? Cannot be 0, 0, right? 2. 0, 2. Okay. Eigenvectors. Just check if these are correct. Okay, all right. Now, how do we now? We have now everything that we need to express this to write the SVD of A. So what is the SVD of A? So what is, so we'll write down these first. What is U? What is sigma? And what is V? It's just this. Is that an orthogonal matrix? What is the definition of an orthogonal matrix? Column should be orthonormal. Columns are orthonormal. There is only one column of length 1, so it's fine. What about V? They have to be orthogonal. It has to be an orthogonal matrix. So what do we do? Are they orthogonal to each other? Are the two eigenvectors orthogonal to each other? How would you verify? Yes, they are orthogonal, right? Because this is a symmetric matrix. So these are orthogonal, so it's fine, but their lengths are not 1. So what? So you do 1 by root 2. Well, okay, let's see. Is it 1? Will it be 1 minus 1, 1, 1 or the other way around? Because remember, the first R rows have to be the ones corresponding to the non-zero eigenvalue. Right, so it has to be 1, 1 minus 1. What is this now? What is the size of this? Size of sigma. One cross 2, that it's P cross Q, right? So it's 1, okay, and what will be the values? 0 first? No. Is it 2? What is the relationship between sigma and lambda? Sigma square is equal, so this has to be root 2 and 0. Okay, so if this is the one, let's verify that in fact U sigma V transpose is A. So U I have to take the transpose of this, so 1 1 1 minus 1. Is that okay? Just verify that this gives you that 1 1. The root 2 cancel. If you take the root 2 here, this is 1 0. Row multiplied, pre-multiplied by this 1 0. That means you're only taking the first row. First row multiplied by 1 is 1 1. So it's okay. Yeah. Here. Yes. This one. Yes. Those are the number of columns. So the U1 matrix has R columns. So there are P columns here, right? I'm saying take the first R columns, call them U1, take the rest of the columns and call them U2. So this is a block row matrix, and this is simply a P cross R matrix, and this is a P cross P minus R matrix. Okay? Okay. Yeah, we won't do another example. I hope that at least gives you some idea about how to go about computing the SVD by hand. Okay. See, okay, if you expand that out, right, to look at the use of SVD or one of the uses of SVD, U2, UR, and then you have sigma 1, sigma R, V1 transpose, V2 transpose, and VR transpose. If you expand this out, what you will get is this sigma 1 multiplied by U1 V1 transpose, sigma 2 U2 V2 transpose, sigma R UR VR transpose. Okay. Each of this is a rank 1 matrix. It's an outer product. Okay. And the rank phase R. Okay. Now, if you look at each of these, right, if sigma R, okay, divided by sigma 1 is very much close to 0. Okay, that means the singular values of your matrix are such that sigma 1 is a large value and maybe the last value is fairly small. Right? That means if the last value is very small, then I can write an approximated version of A like this by simply leaving out the last term, right? Because this is really small, this matrix might not add much value, and the size of these individual terms itself are in a way are all the same because each one of this is a vector with length 1. So each of these matrices itself have similar sizes, okay, or in fact the same size. Okay. So the only thing that determines how big each of these individual terms are your sigma values. Okay. So and because we followed the convention that sigma 1 is always greater than, is written in a decreasing order, the sigma i's. If sigma r is very small compared to, let's say, sigma 1, then a very good approximation of A would be simply the first r minus 1 terms. R minus 1 transpose. What is the rank of this matrix? I'll call it R minus 1. What is the rank of R minus 1? Well, the rank of A was R. I'm asking you, what is the rank of this? Well, one way to figure out is assume sigma r was 0. If sigma r was 0, what would be the what would be the rank of that matrix? So for example, if I simply made this 0, yes, the rank would be r minus 1. So this, what you're seeing here is an rank r minus 1 approximation of the matrix A. Okay. Now, if sigma r minus 1 also was very small compared to sigma 1, then you can knock that out. Then you get a r minus 2 approximation. What if I wanted to rank 1 approximation of A? What can I do? Well, you keep only the first term, you remove everything else, then you get a rank 1 approximation. Okay. Okay. Now the question is, how good are these approximations? Okay. And the reason SVD is popular is because the low rank approximations of matrices that you get with SVD are optimal in some way. Okay. Now, if you have a matrix A, we'll talk about where these low rank approximations are useful later on. If you have a matrix A with rank R, okay, and you're interested in finding out a matrix B that is the lower rank approximation of the matrix A, okay, and let's say rank K. Okay. We're interested in finding out and K is less than R. Okay. A low rank approximation for A, and let's say and how good this approximation is depends on how different are these matrices. If B is a good low rank approximation of A, then of course this difference would be small. If it's not a good approximation, then of course the difference would be big, right? So if we could ask, okay, what is the best possible approximation I can get then? If you want to say best possible, you have to say what criteria you're using for evaluating what is best. If you take the difference matrix and then say, I'm going to use the Frobenius. Well, we are dealing with a matrix, so we need to use a corresponding norm for a matrix. Let's say we use the Frobenius norm. Okay. And the problem here is, so we want to keep the difference between A and the low rank approximation as small as possible, so we want to minimize this. Right? But the constraint is that B, all possible B's that you choose should all have rank K. Okay. So rank of B equals K. Okay. Now, if you search over all possible P cross Q matrices with rank K, and you find their differences with A, and then you take the Frobenius norm of all those differences, you are asking what is the B that gives the lowest value for this difference. Okay. And it turns out that lowest value is simply AK, which is simply you keep the first K terms of your SVD and get rid of everything else. AK is simply sigma 1 U1 V1 transpose to sigma K UK VK transpose. Well, I should not write this is equal to K. The solution that you get is this. Okay, so B will be the solution here. B star, the optimal value for the low rank approximation, is simply AK, that is obtained by just keeping the first K terms in your SVD. Okay, and you could ask, okay, how big is the difference between A and B? Okay, B is not exactly A, that means there is some difference there. You could ask, what is the size? It turns out the size in this case is simply sigma K plus 1 plus sigma K plus 2 to sigma R square these. This is in the note, so you don't have to worry about this. By taking a K rank approximation of A, the error that you incur or the size of the difference between the low rank approximation and A would be simply this. The square or sum of the squares of the remaining eigen singular values, and then it's square. Okay. It turns out that instead of, well, there are different norms that you could use. I've used the Frobenius norm. If you use the 2 norm, the induced 2 norm, okay, it turns out then also the optimal solution is AK. in this case, the difference between 2 will simply be k plus 1. So one of the biggest applications of SVD is to find low rank approximations of a given matrix. Okay. That's all I wanted to say about theory. We'll now move on to talking about where this idea of finding out low rank approximations of rectangular arrangement of numbers or matrices is actually useful. If there are any questions with SVD that we've covered so far, we can discuss it before we start the next module. Okay. I don't know if this is the best spot for this. Everybody can see it, right? Yeah, okay. Okay, see the place where SVD becomes useful is this in applications where you're looking at some sort of dimensional reduction, okay, or you're looking for lower dimensional representation of data. Okay. Well, we started the course by saying we have to necessarily work with high dimensional entities. Primarily when we are talking about data, we have data that has a lot of degrees of freedom. So high dimensional data is a reality in a lot of our applications. And we don't really have a good intuition for high dimension. So often we are looking at, okay, is there a low dimensional representation for my data by nature, or because I want to approximate it because I can't deal with very high dimensional data, right? So there are lots of applications in which you have high dimensional data. High dimensional data for now simply means any situation where you have to measure a lot of different numbers. Okay, so healthcare is a good example, and often, let's see, in healthcare or in other applications, the data that we're dealing with usually comes in the form of a table. Okay, for example, if we are talking about collecting some information from, let's say, patients, from let's say patient 1, you're collecting measurement 1. Measurement 2, so on and so forth, maybe measurement, let's say n different measurements, right? So for each patient, you're collecting n different numbers, okay? And of course, we're collecting data across different numbers. We are interested in something related to the population that we're dealing with. We'll have data from patient 2, we'll have similar data, and then, okay? So often, the data that we deal with then comes in this tabular form. Okay. Or another way to think of this is comes in the form of a n cross n matrix of numbers that we deal with. Okay. This is often the case. Right? Some examples, for example, when you're talking about imaging, it comes in a rectangular form like this, bunch of numbers, and lots of other things. Okay. And some other applications where you often deal with numbers like this. Now, if you're talking about this patient data, right? So one way to think about this data is, well, the features or the measurements that you're interested in presumably tell you some aspect of the patient's health status. M1 tells you something, M2 tells you something different from M1, possibly M3 different from everything else, and so on and so forth. So one way to think of each of this patient records. Okay, so each of my patients is represented by essentially these n numbers. Okay, so one way to think about this data or visualize this data is think of each of these patients as an element from Rn, assuming these are all real numbers. Okay, then these n points that you have essentially reside in a, let's say, n-dimensional vector space. Okay, and there will be points. So each of these points, for example, this point could be this patient. Similarly, this could be another patient here. So this tabular data that you have can be thought of as simply a cloud of points in a high dimensional space, and the dimension that we're dealing with is n, which is the number of measurements that we're taking for each of these cases along the rows. Okay. Now, if you have data like this, and I ask you, what do you think is the dimension of the data? Well, if you simply go by the number of measurements you're taking, say well the dimension of my data is n, right? It resides in an n-dimensional space. But it might turn out, even though you're measuring n numbers, some of these numbers will be correlated to each other. That means they are not really independent, completely independent of each other, right? Because value of m1 might, let's say these two are highly correlated. The value of m1 already determines the value of m2. That means m2 is not completely independent of m1, right? That means they are likely to follow each other. For example, if you're talking about two variables, x1 and x2, and if let's say x1 strongly determines the value of x2, then if you make a bunch of measurements, the scatter of those points is not likely to be like this. It's more or less likely to fall along some curve. Okay, and that curve is essentially the relationship between x1 and x2 because they're not completely independent of each other. So if this is true for two-dimensional case, something like that might be true, is also likely to be true for higher dimensional cases. So the data that we might collect, even though we're collecting n numbers, might not be completely spread out in Rn, but it might actually it might actually have some pattern to it, depending on how these variables are related. Right? Which also means that the data is likely to lie in a lower dimensional space than your original space. For example, if you had, let's say we were dealing with a system which was giving you two variables, x1 and x2. Okay. If x1 and x2 were completely independent of each other and you said a bunch of measurements, first time I might get a value here, second here, third here. If they are not related to each other at all, then you get spread of points. Okay. There is really no pattern to this, right? And the value of x1 is completely independent of value of x2. That means this looks like the system does have 2 degrees of freedom. That means it can choose the values of x1 and x2 independent of each other. But if that was not the case, and let's say x1 was 3 times x2, then what would I get if I make a bunch of measurements from a system like this? Where would the points lie? Well, they would lie, well, if this is the exact relationship and that is what we measure, then they would all lie along this line. So every measurement you make will fall along this line. In this case, even though you are measuring two numbers, the measurements that you're making essentially fall along a line. If this is a relationship, and if the relationship was like this, square, then the measurements I might get will look like this. They will fall along this curve. Okay. In both these cases, right, there is some restriction on my data. That means my measurements x1 and x2 are related by some mathematical function like this or a constraint like this, right? X1 and x2 are not completely independent of each other. X1 and x2, the measurements are in such a way that they satisfy this function, which is 0. That is the constraint. For example, here f would be x1 minus 3x2 is 0. Or the second case, x1 minus x2 square is 0. That would give me this relationship. The first one would give me this relationship. So this could be a constraint. And often when you have constraints like this, what happens is your data now lies in a lower dimensional space, not a subspace, lower dimensional space than your original dimension of the data that you're dealing with. Okay, and in both these cases, so we know this. What is the dimension of this subspace? This is, we're dealing with R2. What is the dimension? So here, your measurement x1 and x2 actually fall on the subspace of R2. And what is the dimension? It's 1. What about this? Is this a subspace of R2? x1 equals x2 square. Subspace of R2? What is the condition for it? So that means here, the bunch of vectors you're dealing with are of this form, alpha square. These belong to R2. The question is, do the set of all vectors that are like this form a subspace? You'll find that it's not a subspace. Well, subspaces should be flat. This is not flat, this is curved. Okay. But let me ask you this, what is the dimension of this space? Here we agreed. It feels like it should be 1, right? Because another way to think of dimension is how many numbers do I need to represent where you are on that surface. Okay. Okay. Here, if I simply measure the distance that you have from the origin, there is one way of saying where you are on the line. I only need one real number. So dimension is 1. Similarly, here, if I come up with a curved way of measuring distance, right, then I can simply measure, take a thread and then stick it along the curve and then say, okay, this is a measure of how far you are from the curve. And if I tell you this distance, and if it's positive, we agree that you always go to the right side. If it's negative, you go to the left side. So if I give you one number, you can still find out where you are on this curve. So the dimension of this is also 1, except that it's not a flat surface. It's some curved surface in R2. Okay. So the point I'm trying to get at is whenever you have a functional relationship like this that constrains your data, then your data is likely to fall on some sort of a manifold. Manifold is simply a general term for a high dimensional surface. A high dimensional surface in R2 is a curve. In 3D space, it's a regular 2-dimensional surface. In 4-dimensional space, it will be 3-dimensional or 2-dimensional, 1-dimensional, all that. Right? So here, if you look at, let's say, the red dots are measurements that we made from an experiment. And when because it's only 3-dimensional, we can visualize what it looks like. It looks like the points are not spread out wherever they want. They fall on this nice smooth surface, right? And because it's a 2-dimensional surface, you only essentially need 2 numbers to describe where you are on the surface. So even though you're making 3 measurements, your data essentially lies in a 2-dimensional surface, and that surface you would like to identify because that tells you something about the underlying physics of the system, because there are constraints between different variables. So it tells you how the system behaves. Maybe you want to lower the dimension because if you have, instead of 3, let's say you had 1,000, okay, but the data actually is only 3-dimensional. Then I don't have to store these 1,000 numbers. I only have to store 3 numbers to know what my data is. So all that, right? So that's the advantage of wanting to know whether or not my data actually lies in a lower dimensional space, even though my measurements are in high dimension. Okay. See, another good example is we live in a 3-dimensional spatial world, but we live on the surface of the Earth. How many numbers do we need to describe somebody's location on the surface of the Earth? What are the 2 numbers that we commonly use? Latitude and longitude. You only need 2. That's because we are living on a 2-dimensional manifold in a 3-dimensional space. Well, there could be people living on the Earth, somebody on a high-rise building, but the size of our distance from the surface of the Earth compared to the radius of the Earth itself is very small. So you could think of it as like this. So some points which are slightly above, even though they don't fall exactly on this surface, the amount by which they deviate from the surface is fairly small. So our positions are very well described by just those 2 numbers, latitude and longitude, irrespective of how far away you are from Earth, because you're unlikely to be too far away compared to the radius of the Earth. Okay? So that's it. So when we say we want to look for a low-dimensional manifold, we'll ask you what is in what low-dimensional manifold is my data approximately distributed in. Sometimes you might find a good approximation, sometimes you might not. Okay? And depending on whether our approximation is good, we decide whether or not the data actually falls in that low-dimensional subspace. Okay? So these are different reasons why you might want to find low-dimensional subspaces. And because we are talking about linear systems in this class, it turns out SVD is very useful if you want to identify low-dimensional planes in which your data is distributed. For example, instead of being like this, if you had, let me just come back to this. Let's say your data was actually spread out along a plane in 2-3 dimensions. We'd like to be able to identify that plane, and that's where SVD comes in. And the technique of identifying low-dimensional flat manifolds is called PCA, or principal component analysis. Okay? And SVD is one way of doing PCA. Okay? Now the question is, okay, you could ask, okay, how do we now find out? Okay? One example is this. Okay? Let's say we're doing measurements in 2D, and we find that the measurements that we're getting are all the red dots that we get. Okay? One way to identify, well, now visually we can say it falls on a circle. Okay? One way to identify what the dimension of this data is to ask, is there a transformation of this data that I can do that explicitly shows me that the data actually falls on a line? the measurements are made in the Cartesian coordinate. Now if I convert each of these into the polar coordinate, right, with the x-axis being angle from minus pi to plus pi, the y-axis being the distance of the point, or the radius of the point, or the distance of the point from the origin. Then if you do the transformation, which is what I've written here, you see that the points actually lie on a straight line. This is to demonstrate that one way to identify easily if our data falls in some low dimensional manifold is to do some sort of transformation. Okay. What PCA allows you to do is it restricts these transformations to pure linear transformations. If you're allowed to only do linear transformations, PCA allows you to identify whether or not your data lies in a low dimensional plane, and we're dealing with only planes because we're restricting ourselves to only linear transformations and not non-linear transformations like this. So that brings us back to this. So instead of falling on a sphere, let's say the points are actually on a plane. So you have three-dimensional space. Let's say the points are all distributed along a plane here. The points form a cloud around this plane. PCA essentially allows you to identify that plane. Okay, and in fact, what it gives you is exactly this. If you take a bunch of data and then you do PCA, it helps you identify the low-dimensional subspace in which the data lies. It also gives you an orthonormal basis for your Rn, in which you can now have a slightly different representation of your data, and it will also tell you how the data is spread out in the different directions. We'll come to each of those. Okay. Let's take a simple example, which we can visualize and understand. Let's say we're doing measurements of height and weight. We know height is related to weight. So if you make a set of measurements, you're not likely to get a blob of numbers all over. The numbers are like more or less, let's say this is height and this is weight. The numbers are likely to be positively correlated. That means if my height increases, my weight is also likely to increase. And if my height decreases below the mean, then my weight is also likely to decrease. So this is what you're likely to get. So we have two numbers. So instead of n numbers here, we only have two numbers. So as before, we follow the convention that the measurements are columns and the different instances of those measurements are your rows. Then let's say we recorded data from 1,000 subjects, height and weight. The first column represents height, the second column represents weight. Then your data is essentially represented now by this 1,000 cross, this m cross n matrix. Okay. And if you do a scatter plot of column 1 and column 2, column 1 along the x-axis and column 2 along the x-axis, this is what you get. Now here you could ask, okay, what is the data really two-dimensional? Well, it depends. It depends on how approximate our answer needs to be. If our answer needs to be very accurate, then of course this is not two-dimensional. But if you're willing to have a reasonable approximation, saying I'm simply looking at is there any relationship at all, then you'll say yes, it's not two-dimensional, it's actually one-dimensional. You only need one variable to say the height and weight of a person. You need one number, not two. Okay. Then the question, okay, how do we identify? Let's agree. Well, we've got this scatter plot. Okay, let's say we have two situations. We have a scatter plot like this. I have another scatter plot like this. And I ask you, in both these cases, which of these two situations has a lower dimensional distribution of the data compared to the other? Let's say this is experiment 1, this is experiment 2. Which one would you say has maybe a lower dimensional representation than the other one? 1, right? Why did you say that? Spread. Somebody said spread. What do you mean by spread? Right, here, if you look at the data, right, no matter which direction you look, the data seems to be more or less equally distributed in that direction. Whereas if you look at this, right, there isn't a lot of data in this direction, whereas here, there seems to be a lot more data. So it looks like there is some directionality to this data. So our intuition of saying that there is probably a lower dimensional structure here compared to here, essentially is based on this idea of how much is my data spread out in these different directions. And that's essentially the principle PCA uses to identify the different directions in which the data is distributed. And it turns out when you do that, you automatically you can use that information to find a low dimensional approximation for your data. Okay? To do that, the first thing you have to do is PCA assumes that your data has zero mean. Okay? So the first thing you do is you remove the mean for your height and your weight. That means this is height, this is weight. You find the mean of that. You find the mean of weight, and then you subtract. That means you simply shift this to the center. Okay. So if you do mean subtraction, you're saying my data is now distributed like this. PCA you should not do PCA without removing the mean, because if you don't remove the mean, your PCA will always report that you have a lower dimensional structure to your data. So you remove the mean. And then the next thing that we need to do is this idea of spread. How do we compute this idea of, well, intuitively we said data is more spread out in this direction. How do we measure that spread? Sorry? Okay, variance of what? Variance of, so here if you mean subtracted, right? So let's say if you take any point here. Let's say this is ith row of your original data matrix X, which was simply X1 tilde. If you subtract the mean is just a single number, a single vector, the center of this cloud. Then if you take the square, well, this is a vector, so you can't take the square. So one way to do that would be, so if you have xi1 minus mu1, xi2 minus mu2. Okay, and you're saying take the square of these, add them, take the square root, or take the square and add them, right? If you simply take the variance of this distributed data, right, what do you get? All you get is the sum of the distance of each of these points with respect to the origin. You don't get anything else. Variance is a single scalar, right? The single number. You will get a single number. It does not tell you the direction in which the data is spread out, right? Because if you have these points and you compute the variance, you will get some value. If I simply rotate it like this and I ask you to compute again, you will get the same value. So that does not tell you anything. Sure, yes. Okay. A simpler idea. Okay. Let's say we don't know what covariance is. Okay, you say we want to find out in which direction, or if there are any directions in which data is spread out more than in any other direction. Okay. Direction is if you're talking about Rn, direction of any vector is given by simply a vector of length 1. Okay. Vectors of length 1 simply tell you direction. Okay. This we're dealing with R2. Let's say we do this. We first choose this vector. Okay. This vector now spans this subspace. Okay. This is W, some vector W. Now I take all my points and then I orthogonally project all of them to this line or to this subspace. Okay. And then I simply find out the distance of each of those projections from my origin, and I compute the square of the distance and I add them all together. Okay. So if I take this subspace and I project all of them, then my data points are like this, and the spread is so much. Now this gives me a single number. Okay. This is one direction. Now next thing I do is I rotate this a little bit, and then now I find out now I project all of the points back to this subspace and I find out how much are they spread out. If you do that, right, and if you, let's say now the direction, because we're talking about 2D, the direction of this vector W is given by the single number theta, 0 to 360. So at each value of theta, we take a subspace that is at angle theta with respect to this subspace. We project all the points onto that subspace, and then we calculate the distance of each of those projections from the origin, and you get a single number. And if we want to find the direction in which the data is maximally spread out, then what we are looking for is the direction of the subspace along which this number comes out to be the largest value. For example, if let's say you plot this, let's say it looks like this, it will never be 0. Let's say this theta star, that's some direction here. We want to, let's say, first identify this direction. Okay. Now we can pose this problem. Well, let me, here, what I just said, find the projection of, if you have any w, let's say it's of unit length, what is the, if I have a point x, how do I find the orthogonal projection of this point x onto the subspace spanned by w? Orthogonal projection matrix. X, that's all. This gives me the orthogonal projection of any point. So let's say this is w. If this is my vector, it gives me this vector. And I want to know the length of this vector, then I simply take. Okay, that is just one point, I. If I now take all the possible points, okay, then I can find the projection of all of these points onto this subspace spanned by w. Now if I simply change w over all possible directions, I'll call this v of w. This is a function of w, because your data points are all fixed. What you are changing is w. So for any fixed w, this number tells you how much is this data spread out in that direction. Now if you change w, because you're talking about R2, so you're simply going along the circle, you find out v of w and you find out the w for which this is maximum. Now you can pose this problem as something like that. So you're trying to maximize this parameter over w1, but with the constraint that your w1 is always of length 1. Okay, that means you're moving along the circle. You're only interested in the direction. You're not you're only interested in identifying the direction. Okay, so that's essentially what I've described to you now. If this is for direction w1, you take the orthogonal projection of xi and xj, and then you're computing the distance of these and summing over all these points. And the solution of this should give me now this direction, right? Because this is what it looks like, data is mostly spread out here. And if you do that, that's what you get. Let's say we'll call, because this is the first direction that we are looking at, we'll call it W1. Okay. The solution to this will be some W1 star, and let's call that P1. Okay. So it will turn out that this is P1. Once you're done with that, you now go ahead and say, okay, I've found out the first direction along which data is maximally distributed. Now, let me go and find the second direction along which the data is maximally distributed. Once I found the first one, I go on and find the next one. But in PCA, you add this restriction. Once you've identified W1, you say, I'm going to look for the second direction, but the second direction has to be perpendicular to my first direction. Okay. Now, if you're dealing with R2, once I've identified P1, the first direction along which data is maximally distributed, the next direction W2, which needs to be orthogonal to W1, is already fixed for me, which is only this. There are no other orthogonal directions in R2. So if you're dealing with the problem in R2, you only have to identify one vector, and the other one you automatically get. But let's say we were not dealing with R2, we were dealing with R3, right? Then let's say this is where the data is spread out. You search over the different directions on a sphere, and you find that this is the direction in which data is maximally spread out. Now, the next step would be then to find out the next direction in which data is maximally spread out. That means my second direction has to be orthogonal to my first one. Now, if this is my first direction, the second direction is anywhere on this plane, right? So now I choose points, different directions along this plane, and then I do the same thing. I project my data points onto each of these directions, and I find out which is the direction along which data is maximally distributed. That will give you W2. If you're dealing with R3, you stop here because the third direction is already fixed. But if you're dealing with Rn, you continue this process. You identify W1, and then you find out W2, which is orthogonal to W1, and then you find the next best direction. Once you've identified W1 and W2, you find the third direction, which is orthogonal to both of them. And then once you've identified that, you find the fourth one, and so you keep continuing. If you're dealing with an n-dimensional subspace, you continue this until you find n-1, and then you're done. Okay, and for each of these directions, of course, we have this number, right? The spread along the direction. So we've identified P1, and then we know a measure of the spread, which is probably this distance, and then P2, this is the spread. Okay. So if you do this procedure, then you get W1, and then let's say we call the spread P1, 1. Okay. This will always be greater than or equal to 0, because Vfx is a sum of distances. Distances are not negative numbers. You get W2, 3, so on and so forth. Well, we don't know what these directions will be, but we know one thing for sure. That D11 will be greater than D22, greater than or equal to. Right? Why is that? D11 is simply how much is the data spread along my optimal direction. Well, that's because the way we've defined the optimization problem, right? The very first one, we are asking, I'll search in all directions in Rn and find out the direction along which the spread is maximum. Once you've identified the direction along which the spread is maximum, the next direction you identify has to have a lesser spread because the direction you've already searched. And you've discarded because that was not the maximum. So D22 will be smaller than this. And because these two are the two possible maximum directions, D33 has to be smaller than the two of them. Okay? And this should already look like something that we saw in the previous lecture, which is, so that's the connection. And each of these directions, optimal directions, I'll not call them W, I'll call it P1, P2, P3. These are called the principal components. Then you can go through the whole details in the lecture slide. I will not go through them. Okay. Well, you can go through this optimization procedure that I've listed here. This is how you solve for the principal components. Another way to do that is you simply take your X matrix. Let's say it's being subtracted, 0 main data. And you take X transpose. No, sorry. X transpose X. Okay. And if you do, this is a symmetric matrix, that means you can diagonalize it. Okay. And if you do eigenvalue decomposition, you'd get an expression like this, because this is a symmetric matrix. The eigenvectors can be chosen to be orthogonal. That means this need not be P inverse, this can be P transpose. Okay. It turns out now the columns of P are the principal components, and the diagonal entries of this are the spread along the different directions. Okay. Okay. And somebody said covariance matrix. So this is essentially this is what is called the covariance matrices are positive semi-definite matrices, or ideally positive definite matrices, and you can show that this matrix is in fact positive semi-definite. Okay. And covariance matrices are symmetric matrices because this is symmetric and also square, right? What a covariance matrix tells you is the diagonal elements. So A covariance matrix simply tells you how is your data spread in n dimensions. Okay, if this is an n cross n matrix. Okay, the diagonal elements, which will always be non-negative, okay, tell you. Let's say we're talking about a 2 cross 2 matrix, right? Let's say this is D11, D1, D22, D12, and this will also be D12. Okay. D11 tells you, so if this is distribution of your data, D11 tells you how much is my data spread along the first axis. Okay. D22 tells me how much is it spread along this, and that's these two. And these two terms, which are symmetric matrix, so this term tells you how much do they vary with us along with each other. Okay, that's why it's called covariance. So these tell you the variance along individual measurements, and the diagonal entry or the off-diagonal entries tell you how they co-vary with respect to each other. Okay, so now if you had a covariance matrix that was like this, 4, 0, 0, 7, then the spread along the first axis is about 4, so the data is spread out like this. Along the second axis, it's like this. And this is 0, that means they don't co-vary. That means the data would essentially be like this. Okay, there would be no linear relationship between your data. But if this was, let's say 3, hopefully this is positive definite, then your data might be distributed. So you still need this to be followed. So your data might be distributed like this. Okay. If it's -3, then the data would be distributed like this. Okay. What would the data be distributed like if this was? It will simply be a circle. Okay. That's the idea. So this idea of how is my data distributed is captured by this covariance matrix. But I think looking at PCA this way gives you a little bit more understanding of what is going on. Great. See, I earlier said that PCA allows you to identify if data falls in on a plane. If your data does fall along a plane, right, then it turns out that there is a way to think about how your data is generated. Okay? Let's say we have, let's say our measurements are like this. Okay? We're working with experiment where we get 2 measurements, x1 and x2. And let's say our measurements actually fall on this straight line. Okay, and let's say our data is distributed like the line where your measurements are distributed, they all fall on this line. Okay, if you see this, then one way to maybe think of how this data is generated is by saying, okay, one possible way to think about this is, let's say this is your x1, x2. What you're observing here, this x1 and x2 is actually generated by some variable z1, z2. Okay, and because we are talking about data falling on a plane, on a flat surface, we can think of some linear transformation that is going on inside this box, that is taking some 2 variables z1 and z2 and generating this x1 and x2. Okay. Now it might look like I've not done anything useful here. All I've said is these 2 numbers are generated by 2 other numbers. Okay, but it turns out that you can make some simplifying assumptions about the 2 generating numbers, and then offload all the structure that is there in your data to this matrix A. Okay, the property that this has, right? If you have these two variables, this matrix has a covariance matrix, or this variable has a covariance matrix which is assumed to be I. Okay, so these bunch of numbers that you're saying generates your data actually comes from a very simple distribution where each of these variables is independent of each other, and they all have the same variance. Okay? That means, say the data are distributed along or within a circle. Okay, and whatever structure you are seeing here, now you offload it to A. You say what is generating it is a completely random process where Z1 and Z2 are not related to each other; they are all operating independently. But these two independent variables pass through some box which is related to the physics of the system. That is then providing this constraint that I see that comes out in my measurements. Right. So, for example, if this was, let's say, x1 equals 4 times x2, then tell me what will be A. What should be my A matrix for me to get this type of data generated by a completely random process? Is that right or no? Here, I'm saying Z1, Z2 goes in, and that produces x1, x2. x1 and x2 are related in such a way that x2 is always 4 times x1. So what should be my A matrix? No, it cannot be a scalar, right? Z1 and Z2 are two different numbers. No, it cannot be. This is 2 cross 1. This is 2 cross 1. This has to be 2 cross 2. Sorry, 4, 0, 0. Okay. Zero, 1 is it? See, then what I get is, see, okay, Z1 and Z2 are completely independent numbers. These can assume any values independent of each other. If you say this, then what I get as my output is 4 times Z1 and Z2. These two are not related to each other. What about this? See, okay, if this is what is produced by my A, this is a one-dimensional subspace, and that is the column space of my A. That means my A has to be rank 1, no? Because the column space has dimension 1. So this has to be a singular matrix. So what about this? If I do 1, 0, is that okay? What I will get out is this 1, I'll get Z1, which is any real number, and then 4 times Z1, which will perfectly fit that. Another possibility is this 0, 0, 1 by 4, 1. Yeah, that is also another possibility. Then I'll get 1 by 4 Z1, Z2, Z2. Both of them are the same. I'll still get all the possible points here. So now all we've done now is we've said, well, the structure in your data comes from this special matrix A, and it's generated by this random process. Okay? That's what I've written there. So you can say that, let's say you're making a bunch of measurements from patients. For any patient, xi, the measurement that you get from that patient is generated by this completely random set of numbers that pass through this matrix A to give me a measurement. Now, for here we obviously assume that both are 0 mean. And if you simply add the mean for the population, then this is your original full data. For example, if you're talking about the height weight data set, then this will be a 2 cross 2 matrix. This is 2 cross 1, 2 cross 1. And this is your average height and average weight. And this is now a reasonable model for your height weight data. Again, you could ask, what is the use? What have we really gained here? Okay? What we've gained is now, let's say I've made 1,000 measurements. Okay? And let's say I know A. And let's say this is the true model of my system. Now, if this is my true model, now I have a model that I can use for generating new data by simply choosing whatever Zi I want, provided that Zi comes from a distribution like this. Now I can use this model to generate new data that I did not measure. Okay, I'll show you an example of that a little later. Okay? But the only restriction is that here Z has this special covariance structure where it's distributed on not really a sphere, but the covariance matrix is the identity matrix. I'm going to skip this for now. I'm going to skip the details. And this view of being able to generate new data, we'll look at that first. Now, let's say we have a bunch of face measurements that we have. This is a popular example. You can go online and then you should be able to find videos on this as well. Let's say we have a bunch of measurements. Okay, we take these faces. Okay, these pictures. Okay, see, picture is a rectangular arrangement of numbers. We're going to do something strange here because we want to apply this PCA. We take each of these rows or columns. Let's say there are n rows and n columns. Okay, we're going to take this, or let's say columns, to make it easier. N column. We take each of these columns and then we stack them all together into a column vector, so that you get an n square cross 1 vector. Okay, so we convert each of those faces into a column vector or a row vector. Doesn't matter. Okay, you convert each picture into an n cross 1 vector. And let's say we measure data from, let's say, 1,000 people. Then you stack all of them together. Then you have your data X. These are the different features. These are the different subjects. Okay. So you first convert this. Okay. And before we do that, okay. If you look at these pictures, right? Is there a node? If you look at all these pictures, there are n square numbers that represent each of these pictures. That means they reside in an n square space. We could ask, does this data fall on a low dimensional subspace in our n square space? What do you think? If I ask you that question, what would you say by simply looking at these pictures? Okay. One possible argument for saying it does lie on a low dimensional subspace is, if the data was purely random, that means each pixel had no relationship to another pixel, then what you should see is this salt and pepper noise in your picture. Okay, because my current pixel has no relationship to my neighboring pixel, but that's not what you see in a picture like this, right? My current pixel is very much determined by who are my neighbors, right? That's one. So that's one clue saying the individual pixels are not completely independent of each other. That means there is a lower dimensional structure here, because pixel I comma j depends on I minus 1, I plus 1, and so on and so forth, right? And in all of these pictures, all the eyes are almost at the same level, the mouth is at the same level, eyes. So one common region in the picture tells you eyes, another common region tells you nose, and they all have a specific, if the eye is here, the nose has to be here. So there is a specific relationship between the pictures. So the data in fact lies in a low dimensional subspace. Okay. Now, because it lies on a low dimensional subspace, let's say we use PCA. There is no guarantee that it lies on a plane. Okay, but we can still use and see what we get. Right. So I take this. Okay. I do the SVD. Okay. And once you have this matrix, it turns out you can find out A from this matrix by simply doing. It's either this is probably A or A transpose. I could be, I don't remember exactly. Right? You take the square, because it's a diagonal matrix of all positive elements, you can take the square root of the individual diagonal elements. Okay. This tells you A. So if I know A, then I can figure out what is my Z. Okay. So this is what I do. From these we figure out some representation for A. And then I randomly sample some numbers Z1 to whatever Zn, okay, where Z1, Z2, Z3, Z4 are independent of each other, and I simply pass it through A, and what comes out are these pictures. Okay, so you started with a completely random set of n numbers, and once you pass it through the matrix A, what you get is what resembles a face. Right? And these are all pictures that were generated completely randomly using that data set as a representation for how this process of generating face pictures works. Okay. See now, what comes out here is entirely. This does not mean that matrix A holds the ground truth about how faces look. A simply carries information about the pictures that you gave it. Okay, so using whatever structure was there, whatever linear structure was there in that set of pictures that you started with, you identify P and D. From P and D, you can identify A, and from that you can now generate new faces. Okay, so this whole idea of generative modeling and stuff, this is the simplest possible generative model that you could come up with. Okay, so that's the idea. Okay, now let's go get to the second point. I only have 5 minutes, but I'll go through it quickly. So this is one of the uses of PCA, where you can use it as a generative model for generating new data. Okay. And in the previous case, of course, the faces don't look as realistic or clean as the other images, because I am not, well, first of all, that's because the faces, of course, don't fall on a plane. They have a more complicated structure. And what I'm generating is an approximate version, but I'm saying I'm going to only worry about generating the linear, reproducing the linear structure and not the non-linear. So that could be an explanation as to why, well, this face does not look like a realistic face like that. Okay, or it looks like a very low-dimensional approximation of that because it's all smudged out. Sorry. Right. So that's one of the applications of PCA. Another application is, let's say you have a situation where your data is, what you measure is like this. You can use PCA now to compress the data. Okay. Now, if you did PCA here, the first direction would be along here, the second direction would be along here, but D11 and D22 would be drastically different. So in this case, D11 would be, let's say, around 10. D22, which would be this distance, would be less than 1. So now, if you simply drop the D22 term, okay, so here, so if you expand this out, right, what you will find, so X transpose X, if you simply expand this, what you will get is D11, P1, P1 transpose, D22, P2, P2 transpose. If D22 is very small compared to D11, like in that case, you simply ignore this. Now your data is essentially all represented along this line, then you only need a single number to represent your data. So now you don't have to store two numbers to represent this data, you only store one number. That's one way of compressing your data. Okay, and of course if you say all my data lies along this straight line, you are making an error, and the size of that error will simply be, one measure of the size of that error is simply how much variance did I lose by ignoring the second term there. That's simply D22. Well, that is for a two-dimensional case, and we're getting a one-dimensional approximation. But if you were talking about data that is n-dimensional, that means you do have something like this: Bnn, Pn, Pn transpose. If you wanted a k-dimensional approximation of the data, then you simply only keep terms till dkk, and then you get rid of the other ones. Then the error that you would make would simply be the sum of the variances from k plus 1 to n. Okay, that's for data compression. Okay, that's this. Okay, this is a slightly different way of working with pictures. Okay, we have a picture like this. Here, we only have a single picture. Okay, and we treat this as our x. Okay? These are our rows, these are our columns. Okay. Now, if you do SVD, okay, which is I'm not talking about principal components now. SVD, but you can use SVD to do the principal components. That's explained in the slides. You can go and take a look later. Okay. If you do SVD on this, let's say this is a P cross Q matrix. So you will get U sigma V transpose. So you will get this. Okay. And you will get a bunch of singular values. Right? I can't remember. So here, you can get up to 1,208 singular non-zero singular values. But if you do the SVD and you plot the singular values, sigma 1 to sigma 1208, you'll find, so this is 1, 2, 3, 4, starting from 1, this is 1208, we'll find that the singular values will immediately drop like this. Okay, beyond a particular point, the individual singular values are fairly small. Okay, so only the first few, let's say I can't remember what, let's say first 48 maybe, have a fairly big value, everything else is 0, right? Then we could ask, okay, what if we try and find a low rank approximation of this picture? Okay, remember what we talked about in SVD? This is equal to sigma 1 U1 B1 transpose, so on and so forth, sigma R UR BR transpose, right? Let's say we say, okay, I want a one rank approximation of this data. Okay, and we simply increase the rank that we want. Okay, if you only keep the first term in that SVD, you get something like that. Of course, you won't see anything. But once you start increasing the rank, right? Once you get to about, well, I've done up to 150, up to 80. 80 also is good. Yeah, 80 is good. Okay, that means you simply keep the 80 terms here and you neglect the rest. You already start to see that, at least visually, the picture is not as good as the first one, right? And once you get to about 150, it's nearly indistinguishable, at least for the human eye, right? So what this means is, even though here to store this picture, you had to use 1028 cross 1880 pixel values. What the SVD has told you is, you don't see the potential possible singular values is this, but with just 150 you can essentially store the entire image, right? That means you've already lowered your requirements by 10. Right? So another application of SVD is essentially for compression of your data. Okay? This again is made possible because this data lies along a lower dimensional subspace. Okay? And SVD allows you to identify that structure and do a compressed or have a compressed representation for your data. Okay, that's all I had. But before I conclude, right, this principle. So we talked about the importance of variance, the spread of the data itself. You could ask, well, do these directions have any meaning? Spread tells you how much variation do I see in that direction. You could ask, do the directions themselves say something? Do they have any interpretable meaning to them? Right? It turns out sometimes they do have. For example, if you take the face data and then you do the principal component analysis and you look at the very first principal component, I'm simply showing here what happens if you increase the amount of principal component 1. This is the original image, and you decrease the amount of the principal component. In this particular case, it looks like the principal component 1 simply tells you the amount of intensity in the picture. Okay, increasing a principal component decreases the intensity of the picture, whereas decreasing it increases the overall intensity of the picture. So the data has found out that the largest variation that I see between the different pictures is just their change in the amount of intensity in the picture. That's one. Now, here, you might not agree with me on this. Here, if you look, so this is the original picture. Look at what happens when you go to the right or to the left. Okay. One possible interpretation of this is the amount by which the person, it looks like the person is smiling. Okay. The pictures on this end would look like is maybe smiling a little bit more than the pictures on that end. So because you had this picture where you had different people, either not smiling or smiling, in this data set, the second largest variation has something to do with whether the face's lips are curved up, straight or down. That's one possibility, right? So here, for example, at least if I squint my eyes, it looks like this person smiling more here than there. This person as well. So that is maybe one possible thing in your data set. That this could be related to that. And a few others, again, I could be fishing. Maybe there are pictures here where in some of them people have glasses and some of them people don't. If you compare the left hand side with the right hand side, you do see faint traces of specks being put on each of these pictures. So maybe PC4 captures this idea whether or not the picture has or the person in this picture wears spectacles. So there is a way to interpret these. You might not be able to find a good meaningful interpretation all the time, but in many applications people do find that the PCs tell you something about the underlying factors that determine how the data is distributed. Okay, that's all I wanted to say about STD, and that completes our the portion on linear algebra. I was planning to do probability and stats after this, but what we will do is instead we'll shift that to the end. We will then move on to optimization from Monday. Okay, so we won't come back to linear algebra again. We're done with all of that. But if there are any questions, please bring it up next week, Monday, and then we'll discuss them, and then we'll move on to optimization. Okay. All right. Okay. Thank you.